From last time. So what type of integral is that? It's got a name. It's definite integral. So uppercase f is simply the antiderivative of lowercase f. And we simply evaluate the uppercase f at b, uppercase f out a, and then we subtract to get the definite integral. It's always going to be a number. Before I write FTC1, FTC, Fundamental Theorem of Calculus, a couple of properties. If you have a definite integral integrated between a and b, it will simply equal to the negative of the integral from b to a. Now, b is the upper limit, a is the lower limit. This number has to be bigger than that number. But if we switch, then you will get a negative. Good. Once again, we have to integrate from a to b. I could write this as integral a to c f of x dx plus c to b f of x dx. What is the integral? What does it give us? Area under the curve. So suppose I have some curve and I want to find the entire area under that curve. In other words, a shaded part over here, or about to be shaded part. I can arbitrarily pick a point C between A and B. The area from A to C, which is this part, added to the area from C to B, gives us the total area under the curve. Do we agree? Yes. Yes. So finding the area under the curve from A to B is the same as saying I'll find the area from A to C, then C to B, add them together. That's exactly what this means. Area under the curve from A to B is equal to the area under the curve from A to C added to C to B, provided C is between A and B. Good. Two important properties. So the antiderivative of that function, f of x, is the integral of that function. And we know that if I take the derivative of uppercase f of x, I will get lowercase f of x. The fundamental theorem of calculus is going to show us why. Calculus 1. That's fundamental theorem of calculus. to do that, let's just consider integrating the function f of t between a and x. Good.
Wouldn't that be t or f of t, the big F?
For the
This one?
Yeah.
No. I'm about to get it. So this t is what we call the dummy variable. Mind you, once I integrate and plug in the upper limits and lower limits, I'm going to get a function of x. Yes? Which is why this is x and that's t. You don't get this x until you apply exit. What is the derivative f prime of x by definition? Going back to unit 1.
Just taking the derivative
Yes, but what would that equal to?
integral of t.
This is unit 4, going back to unit 1.
Oh,
Definition of derivative.
it's interchange.
Okay, f prime of x would become f double prime.
Isn't like the f something x plus h, the minus like that?
Keep going.
Difference quotient.
Okay, thank you. So f of x plus h minus f of x divided by h. That is the difference quotient. And of course, we have to take limit h approach. Good. In some literature, this function, the way we wrote it, is also called as an accumulation function. In some literature, I mean statistics. So I know this, so I have one part here, uppercase f of x as that. What would uppercase f of x plus h be?
Would it be x plus t?
I have the definition for f of x. I would like to know what f of x plus h will be. In terms of the integral.
Would it be like integral of, the x to a, f of t, dt plus h?
Okay. I like how you break things. Very interesting.
I mean, f of x is that plus h, and that's it.
Right here.
Yeah.
Why right here, Jay? Of all the places you can add x, why did you add it here?
Because it's blank right there. Like you left it purposely there.
I left it blank so that you can tell me the answer.
Oh.
He's trying really hard. Caitlin, go ahead.
Well, do you add it to the x?
Exactly, you add it to the x. Good so far? Can I erase the top over here? Uppercase f of x minus uppercase f of x plus h. Those two. I can write it as integral did it backwards, I'm sorry. Because I could have put a negative one. T is the dummy variable. Dummy variable, substitution variable, all the same, but in this context, it is the dummy variable. What would happen if I switch the limits?
It becomes positive.
This would become positive, right? So good so far.
So why exactly did you flip it? So we can-
From the same one earlier. A to b f of x dx, if you switch the limits, it is minus b to a f of x dx. So the negative times negative will give us positive. Good. Now, the second property, if I use that, how can I rewrite this? A is definitely between x and x to h. X. If you go back and look at that property, A is x, B is x plus h. I picked a point in the middle. Yes. So I can write this as from x to a point in the middle, or not necessarily exactly in the middle, somewhere in between, and from A to x plus h. They are all in the same. Good. I am going to erase that. I know what f of x plus h minus f of x is in terms of that integral. And now I'm going to divide by h on both sides. So if I took the limit h approaches 0 on both sides over here,
So nothing happens to that h at the top.
it's just that because I'm trying to come up with this expression on the left-hand side. So the right-hand side will simply become f prime of x, uppercase f prime of x. Keep in mind uppercase f of x is also called as the accumulation function. That is the derivative of that accumulation function. The derivative of this from 4.9 would be f of x, because derivative of the antiderivative is f of x. There is a rigorous proof as to why this would become what it's about to become, but I'll illustrate it visually. Yeah, it's easy to understand that way. Otherwise, I've got to use mean value theorem, extreme value theorem, squeeze theorem all the time to get to that final step. If you're interested, come talk to me. So that is my function, f of x. Good. The area between x and x plus h is simply the difference over here, f of x plus h minus f of x. Do we agree? Now, what would happen to that area as I bring h closer and closer and closer to x? Huh?
It gets smaller?
It's going to get really, really small. Agreed? Yes. So let's say I made h very close to 0. And I'm right there at that point. Good. I can write f prime of x, which is the limit h approaches 0. One over h. Very, very, very close to each other, but still apart by the amount h. Do you agree? Very small, but still there's a h. Awfully drawn rectangle, but it is a very, very thin rectangle. Agreed. What is the area of the rectangle? H times height. Since those 2 points are very close to each other, I can approximately call it as f of x. Do you agree? Very, very close to each other. So that tiny little area from here, I can write it as h times f of x.
Where did you get the 1 over 8?
Oh, it's right here. Right? So the left-hand side is f prime of x. Right-hand side, I have the 1 over h part. When I take the limit, getting closer and closer, I'm getting a very thin rectangle. And that area will be h times f of x. What would happen to the 2 h's? Well, cancel. Yes, derivative of the antiderivative is the function f of x. Does that make sense? Now we can write this as, of course. Just because I know can be shown this approximation will become an equal identity. We use coordinate theorems. But that's great and all. I take the derivative of the antiderivative, I get the original function. We know this from 4.9. What's so new? In terms of the accumulation function, the rate at which this area changes. In other words, let's say I start here. go that way, keep on moving with some rate, yes? What is happening to the area as I go from, say, from here, right here, beginning, all the way up to that point? What happens to the area? It gets bigger and bigger and bigger. As I move a little bit further, what happens? Something's getting taken away, right? The rate would reduce the area. The rate, not the actual area. The area is getting bigger, but the rate at which it changes, it's going to be really rapid here. It's going to decrease a bit, and then it'll increase. So all that means is that the rate at which the accumulation function changes, in other words, the rate at which the area under the curve changes, is purely defined by the function itself. Does that make sense? So FTC1 simply states the rate at which the accumulation function changes is purely defined by the function itself, f of x. Great. Can I erase? So when we first started, all of that, I had f of x is equal to integral a to x f of t dt. Agree? And I showed that taking the derivative of that will give you the function f of x. Done. Good. How do I go about this? Suppose integral at x. My favorite color is popping up, but it's not going to last long. A to u, and u is a function of x. Good. So f of x, instead of calling it as a to x f of t dt, I'm going to call a to u f of t dt. But do keep in mind, u is g of x. Good? Now, if I use the theorem, I'll leave that up there. I want you to tell me what f prime of x will be. Instead of a to x, that gave me f of x. Now I have a to u, f of u. Let me not skip this step. What would f of x be? F of g, close. Or f of u, you are correct. Yes. But what is f of u then? G of x. But keep in mind, we are taking the derivative of not just x, rather a function of x. So what should we do when we take the chain rule? We multiply it by u prime. Good. So if the limit happens to be a function of x, we just use chain rule to get that. Been mentioning U-substitution for a bit. So we're not going to do U-substitution, but if time permits, I'll go over it just for fun. So that is the fundamental theorem of calculus, do we agree? Now, if I integrate with respect to dx, side note. I can't simply integrate on one side. I have to integrate on both sides. And that's exactly what I did. From last time, integral and derivative will get cancelled. Correct? Inverse operations. So that would simply become f of x. The integral of that function. So when you get to U-substitution, if you have a function of a function and you have the derivative of that inner function in an integral, that is an indicator that you should use U-substitution to integrate. The key lies right here. Function of a function, and what is the function that's within the function has its derivative over there. That will tell you you've got to use U-substitution.
Can we
Oh,
see a
wait,
problem?
huh?
Can we see a problem here?
Yeah, we'll do it later. What if time permits? I don't want to get to U-substitution. Are we clear?